Hi, I'm Spoon, and in this presentation I will be going over how I prove to myself that light is in fact a wave. Of course, I've been taught that, it's just I never really thought much about it and assumed it to be true. And so because of one physics class, I became curious and just double-checked that. And thus begins my presentation on that whole process. As a disclaimer, light isn't completely a wave, but I will be focusing on the wave-like properties of light for the remainder of this slideshow. Alrighty, so a couple years ago I took Physics 2, which covers electromagnetism. Light is an electromagnetic wave. And in one of the labs that I had to do, I had to shine a laser through a piece of cardboard with a small slit cut through it and see what's projected. Following my past intuition, I thought that when I looked on the other side, I would just see basically like this laser dot shown on the slide, which I'm using as a laser pointer. But instead of being a nice dot, it would be kind of cut at the edges to make sort of a rectangular shape following that shape of the slit. But no, it produces a barcode, which is crazy, but it's actually not crazy because that's just how light works as a wave. Now to go over a few things to consider about waves. For one, waves can be added together. You can think about how if you have one speaker producing sound waves and another speaker producing sound waves, those sound waves add together and now the sound is louder. Same goes for having one versus two flashlights producing light waves, or if you have one or two people producing waves in a pool, now there's just more, sometimes larger waves. And this is shown here. You have one wave, you add another, now you have a bigger wave. But not in all instances, because if you add one wave, shown here, plus its inverse, as shown here, then you can get a weaker wave or no wave at all. So waves can add together to create stronger or weaker waves, depending on how they're oriented. Now, as an interesting source of light waves, lasers. Lasers produce coherent light, which means it's monochrome and all has the same phase. Monochrome means one color, and so all light produced from a laser has one wavelength, or a very narrow band of wavelengths. Over here you can see incoherent light. They're all different colors, different wavelengths. Smaller wavelengths mean that light is more towards the blue spectrum, and larger wavelengths mean that light is more towards the red spectrum. I had to manually color code these, but they're all different wavelengths, and they're not all in the same phase. If you have two light waves of the same frequency, but their peaks are not lined up, that means they are not in phase. Whereas over here, you have light waves of all the same wavelength and all of their peaks are lined up, which means it's coherent light. And this is the kind of light that would be produced from a laser. Finally, one thing to consider is Huygens' principle. Put simply, waves propagate outward in all directions, or at least that's kind of just what they want to do. If you have a barrier, it's going to go around the barrier, and once it passes, it's just going to go in all directions. For instance, if you have a barrier with a small opening and you have water waves passing by, they'll get bounced off of the barrier, but where there's an opening, it'll pass through, and then it'll spread out in all directions, not just following kind of this way, but also like up and down, rounded. And this starts to lead to the single slit experiment I did that shows how light interferes with itself and adds together to create interesting patterns when passing through a small slit opening. All right, so let's look at this with some modeling using Octave Online. I've provided some code that I used here if you want to try it yourself. And Octave Online is free to use and online, so it's really convenient. Alrighty, in this image here you can see that I am simulating a point source of light. This red asterisk shows the location of the point source, and you can see that the waves are propagating out circularly and are being attenuated with distance. Now this is all manually coded. I have it so that this is all circular and it's getting darker the further away from the source. But I'm more interested in how these point sources add together. So if I have a line of these point sources and I stack them on top and add them, then I get this interesting finger-like pattern. And then there's this beam down here, which is very interesting because that correlates with the single slit experiment I talked about earlier. If you have all these wave light point sources here in a line, when they come out, they propagate outwardly, but they interfere with each other to produce this single beam here and this barcode that comes off. And that kind of explains how a laser is able to produce a beam of light, because if it's propagating outwardly, then how does a laser kind of create this like nice straight beam of light? If you look here, if you have a line of point sources, you have this single beam out, which corresponds with the dot that's produced with a laser. And then there's also these finger-like beams coming outward like this. And this can be seen with a typical laser. Here I have a small GIF of me pointing a laser at a piece of paper and slowly bringing it closer. You can kind of see that there's like these little rings around which correspond with these little beams sticking out if you like imagine this as 3D. After that lab, when I came home, I was thinking I kind of want to double check that nothing screwy was going on. I mean, I didn't really think about it, but I didn't think there was anything screwy going on, but I just wanted to like try it myself to be like, yes, light actually is a wave. It's not like it was just a special instance in that lab with the nice fancy special equipment. And unfortunately, I did not have the nice fancy special equipment. I had a laser pointer and some household items such as playing cards and a piece of paper, which is a little tricky to set up. But here you can see I have a desk in which its surface is about, actually I'm at the desk right now, it's about like a meter off the ground. And then I have two playing cards right here, which act as the barrier with a slit opening. And then I have a 405 nanometer laser, which corresponds to blue light, which unfortunately makes things difficult. Because red lasers produce light with a larger wavelength, that means it's kind of easier to see the pattern produced when passing through a slit, because everything is more spaced out when using red light. Any case, these are the results I got. Over here on top you can see a GIF of me slowly opening and pushing closer the cards so that the slit gets wider and smaller. As the slit gets smaller, it kind of looks like the laser point is spreading out, and then as they make the slit larger, then it kind of condenses back more towards the nice little point that is produced by a laser. And here I have a nice image showing that diffraction pattern. You can see the kind of the center beam, and then there's these dots being produced, which corresponds to that, what I described as like fingers sticking out from the beam. And so this is how that whole barcode is being produced. Just for reference, I put this image on the previous image of the setup, where this line of light is perpendicular to the direction of the slit, which, again, following my typical intuition, is really weird, but that's just how light waves work. Now, if you want to prove to yourself that light is in fact a wave because you don't believe anything I said in this presentation, go for it. But also remember that lasers present some hazards. For instance, you don't want to burn your retina, so don't look into a laser, please. Don't point it into things like cameras because you can damage electrical components. If you want more information, you can check out OSHA. I have the link here, which covers some laser hazards. All right, thank you for watching this video. Hopefully, if you didn't know much about how light waves work, maybe you know more. And now you have a better idea how you can prove to yourself that light has wave-like properties. And yeah, have a great day.